Question for capacitors. A capacitor with air between the plates has capacitance of 3.0 times 10 to the minus 6 farads. That's 3 microfarads. Calculate the capacitance when a wax of dielectric constant 2.8 is placed between the plates, and then state your assumption. So the first part is relatively easy because we have the capacitance formula, C equals dielectric constant times the absolute permittivity of free space times the area of overlap of the plates divided by the distance of separation of the plates. Now without the air, this term doesn't exist. Sorry, that's with the air, that term doesn't exist without the dielectric. But with the dielectric in place, we have to multiply the whole thing by that dielectric constant. So before, with just this section, it's 3.0 times 10 to the minus 6. And then we have to add this bit in, so it's going to be times by the 2.8, because that's a dielectric constant, and it equals whatever it equals, 2.8 times 3.0 times 10 to the minus 6. So that's how you solve. I'm not getting into the details here. B. We are now asked to explain how a dielectric material creates an increase in capacitance. So this is a little bit of a tricky one, and it relies on your understanding of the dielectric material and charging by induction. So if you remember, you've got a capacitor, and when you charge it up, you have charge stored on the plates, one negative, one positive, plate that is, and then we stick I'll use a different colour for this, a dielectric material inside of it. Or I've actually forgotten something in the top one, but I'll go back to that. We've got dielectric material inside of it. Okay, we're being asked to explain how that dielectric material increases the capacitance. Well, in the same way that if you bring a charged object near to an insulator, the surface electrons can move, which means if this is full, the electrons will be attracted to the positive side in any case, leaving a positive charge behind. So we'll have this charge separation as the electrons are attracted to the positive. Overall it's still neutral, overall it's still an insulator, but the surface, these electrons on the surface have moved, and you have now polarized the, depending on which country you're in, this will be a Z or an S, we have now polarized the insulating material. Same thing with the dielectric in the middle here. We now, we've got a whole lot of positive charges on one side, which will attract electrons, and negative charges mean that side will be attracted by, will cause positives there, and it's kind of working together to make it occur. This side drives away electrons across that way, and this side attracts the electrons. In any case, you have polarized dielectric in the middle, and if you consider the two electric fields, you've got the electric field, I'll draw this in purple since it's in purple, the electric field of the capacitor plates itself in that direction, and you have the electric field of the dielectric material in that direction, and that's going to overall reduce the electric field on the inside. So your electric field decreases. Really important. So now that you've got a decreased electric field, that means the voltage across this capacitor has had to decrease, because you remember the voltage depends upon the electric field. The electric field depends upon the voltage, depending on which way you look at it. The electric field is the voltage over the distance of separation. Distance hasn't changed in this case, but our electric field has decreased, meaning electric field strength decreased, meaning the voltage had to decrease. So in this case the voltage is decreased while storing the same charge. So the charge is still the same on the capacitor. So that means for Here's our capacitance formula. Sorry, I've got this back to front. Charge per voltage. It's a little bit unclear, but our voltage has decreased while the charge has stayed the same, meaning the capacitance has increased. So that's that formula explaining how it works. Okay, now the thing I missed up the top was that we were asked to state our assumptions. I guess the assumption is that everything else is remaining constant, so the distance separation is remaining constant, absolute permittivity of free space can't change, and the area of overlap of the plates is still the same. You would also assume, I guess, and this is coming from the answers, I wouldn't think of it myself naturally, to be fair and honest, that when you put this dielectric material in the middle, you're assuming that there's no air gaps or anything, that it fills up the space completely, that it's a perfectly solid block of insulator, I guess, with your plates firmly placed and to the side with no gaps. But yeah, everything else has to remain constant. That's very important. And that's that for this bit.